Hey everyone, welcome back, and today let's solve Leetcode problem 875 titled Koko Eating Bananas. So Koko loves to eat bananas, and there are n piles of bananas where the ith pile has piles at I bananas. The guards have gone and will come back in each hours, and Koko can decide her bananas per eating speed of k. Each hour, she chooses some pile of bananas and eats k bananas from that pile. And if the pile has less than k bananas, she'll eat all of them instead and will not eat any more bananas for that specific hour. So Koko likes to eat slowly but still wants to finish eating all of the bananas before the guards return, and we have to return the minimum integer k, or basically her eating speed for bananas per hour, such that she can actually eat all the bananas within h hours. So in example 1, we have the input array piles to be 3, 6, 7, and 11. And we have 8 hours to eat all the bananas in every single pile. And we would output 4 because that would take exactly 8 hours to actually eat all the bananas, right? And that's the minimum value of k to actually eat all the bananas within h hours. In this case, 8 hours. Right? And the reason why it takes 8 hours is because to eat 3 bananas in the first pile, it takes, of course, 1 hour because 3 is less than 4. For 6, it's going to take 2 hours, and for 7 is also going to take 2 hours. Basically, because she takes 1 hour to finish the first 4 bananas of each pile, and then to finish the remaining bananas, she's going to take another hour, which is going to take 2 hours for each respective pile, and for 6 and 7. And for 11 bananas in the last pile, she's going to take 3 hours, okay? And so, since this takes 3 hours, these two take 2 hours, and this takes 1 hour, the number of hours that we need total is going to be 4 plus 4, which is equal to 8 hours, which is less than or equal to 8, right? And in example 2, we have the piles input array to be 30, 11, 23, 4, and 20, and we have 5 hours to eat all the bananas. And since the length of the piles, or basically the number of piles we have, is equal to the number of hours we have, we know that we can only spend 1 hour to eat all the bananas in each pile, and so for that reason, we'd have to return the maximum value of piles, or basically the pile with the most number of bananas, because we're guaranteed that that's eating speed k, that we can basically eat every single pile of bananas in 1 hour. And finally, in example 3, we have the piles input array to be 30, 11, 23, 4, and 20. And we have 6 hours to do that. And we'd output 3 because that's going to take, we'd output 23 because at that eating speed k of 23 bananas per hour, we would take exactly 6 hours to actually eat all of the bananas within 6 hours, right? We take 2 hours to eat 30, and we take 1 hour for the rest, and 4 plus 2 is 6, which is just perfect because it's equal to the number of hours we have. So note that there is actually an inverse relationship between k and h, where as the speed k decreases, the number of hours we take, or h, is going to increase, because as we eat less bananas in each hour, or basically as our speed decreases, the time we need to actually eat all the bananas increases, right? It's an inverse proportion, right? And basically, we want the number of hours needed at any speed k to be as close to h as possible, because we want to minimize k and basically get h to be as close as our input h as possible, right? Because we want to return the minimum integer k as shown in the problem statement above. So with that out of the way, I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would optimally solve this problem. Okay, so essentially to solve this problem efficiently, we're going to be using the binary search algorithm. And the reason why we do that is because the possible speeds range from 1, which is the slowest possible speed, to the size of the largest pile, which is the fastest possible speed. And if she eats an entire pile an hour, that's going to be returning the maximum pile, right? So this basically gives us a well-defined search space, right? So basically, the number of hours required to finish all the bananas is monotonically decreasing as the eating speed increases. So that basically means if eating at speed x requires too many hours, eating at a higher speed, per se x plus 1, will also be too fast. And similarly, if speed x is fast enough, then any higher speed would also work for that reason. And this is actually perfect for binary search because that basically requires a sorted or monotonic sequence to work optimally. So of course, a brute force approach would basically test each possible speed from 1 to the maximum pile size, but binary search of course reduces this to logarithmic time, making it a lot more efficient, right? For any of you guys who know runtime complexity, binary search is actually a big O of log n algorithm, which is very optimal and very efficient for many different problems like this. So essentially for the solution structure, we'll use binary search to minimize the eating speed. And we basically have to check if Koko can finish all the bananas in the given hours at current speed k for any iteration in the binary search algorithm. Okay, So the way we're going to do this is we're basically going to initialize our two standard pointers in the binary search algorithm like we always do, our left and right pointers to be initialized to 0 and the length, or not length, but rather the max of the piles. In fact, there should be 1, not 0, because the reason why it's 1 is because we have to initialize left to be the slowest possible speed, which is 1, and right, or basically the R pointer, has to be initialized to the largest possible pile, which is the fastest possible speed, if we only have 1 hour to actually eat every pile. And this basically sets up the search range for the binary search algorithm because we know that k is going to be between these two values, L and R, which are initialized to the 1 and max of the piles array. Okay? Once we do that, we're going to have our standard while loop for the binary search algorithm. So while L is less than or equal to R. Again, what this does, if you guys aren't aware what the binary search is, this basically starts a loop, a while loop that will continue narrowing down the possible eating speeds, and the loop basically runs while the left or L bound pointer is less than the R bound. Okay, so while L is basically in bounds of R, right? So we'll set our potential k value to be the L plus R integer divided by 2, basically the middle value like we have in standard binary search algorithms. And basically, we'll calculate the middle speed k between the current left and right boundaries, and that's going to represent the candidate eating speed that we want to test for this iteration in this while loop. Okay, once we do that, we'll have the number of hours to be 0 for this iteration. So, and then we'll loop through all the different piles of bananas in the piles array. And we want to increment the number of hours we take for each pile to basically be the math.ceil, basically rounding up every single pile and the number of bananas it has divided by our current speed k for this iteration. Okay? Again, what this really does is once we initialize our k or middle value, that current speed for this iteration, we want to set the number of hours so far to be 0 because of course we haven't traversed through the array yet. And after we set hours to be 0, we'll loop through every single pile in the piles array, and we'll increment the number of hours we take for each pile to basically be the number of bananas there are divided by k, and we have to round up, right? Like the problem says, we have to round up rather than rounding down, and we can do that with the math.ceil method. Okay? And again, essentially why we have to round up is because, take per se 6. 6 divided by 4 rounded down is just 1, but we would still have 2 extra bananas after requiring 1 hour to eat the first 4 bananas, and we have to consider those 2 bananas to be an extra hour, right? Because we need 1 more hour to actually finish off that pile, and so we'd have to actually round up to account for any leftover bananas after any hours, right? So once we actually increment the number of hours for each pile, now we actually have to check if the number of hours we took for this current speed k, if that's less than or equal to h, that means that this is a valid k value, right? And then we can set our resolution, which is ultimately what we want to return, the minimum value of course, itself, because we don't want to make it larger, and k, basically the current speed for this iteration. And I actually forgot to declare res. I'll just declare that up here. And this is going to be initialized to the worst case possible, which is the maximum value of piles, right? And of course, if we don't find a faster or quicker speed, k, to actually fulfill this criteria, then we just simply return the maximum amount of piles, because that would signify that h is going to be equal to the length of the piles for any test case like that. So again, if the number of hours of this iteration is less than the h input, this is a valid solution, and we can set the number of hours so far that we've seen recorded so far to be the minimum value of course, because we don't want to make it larger, and k, basically the speed for the current iteration that still works and passes the criteria to actually eat all the bananas within h hours. Right? Once we do that, we want to actually get r to be mid minus 1. And the reason why r is mid minus 1, again, for standard binary search, we know that this is already a speed that we can already work with, right? It's already fast enough or large enough of a value or speed to actually eat all the bananas in time. And so we want to actually explore smaller values of k that still potentially help us or enable Koko to eat all of the bananas within h hours, right? Basically explore the left part of the array like we do in standard binary search. And then we'll have an else statement here that basically checks when hours is not less than or equal to h. That basically means when hours is greater than h. Then basically the k value for this iteration is too small, and we need to have a faster speed to be able to eat all of the bananas within h hours. And so we'll set L to be mid plus 1 to explore the right half of the array, or basically the larger values, right? Okay, and once we do that, we can ultimately return res, because it eventually will have stored the minimized value of k such that we can actually eat all the bananas, or all the bananas in the piles, within h hours. So we can just return res. And unless I made any syntax errors here, this should actually work, and this should be accepted. Okay, yeah. Okay, so this should actually be k. And the reason why is I set k to be L plus r divided by 2 rather than mid, right? Just a quick typo by my part. But now this should actually be accepted. And as you can see, it's just about as efficient as you can get. Okay, so for the time complexity here, of course, this is going to be big O of n log m, where n is the number of piles, since we iterate through each pile when checking if Koko can actually eat all of the bananas. And log m is the time for the binary search, where m is the largest pile size. And that's basically because we perform a binary search on the range of speeds from 1 to the largest pile size. And of course, for the space complexity here, this is going to be big O of 1, or constant time, because we use the constant time amount of extra space since the main work is done in place with the variables left, right, and mid basically just being initialized to integer variables rather than any extra data structures for our input, right? So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.